Hello everyone. This video is a demonstration of how to simulate CV. This documentation provides step-by-step guides on implementing the cyclic voltammetry model. Here is the content. The main steps are in the model implementation, and this is for the reduction reaction. After several modifications, we can get the oxidation reaction. After finish these tutorials, what you can get is the potential time function and also the CV for reduction reaction. And of course, you can get the corresponding potential time function and the CV for oxidation reaction. So let's go to the model implementation and implement our CV in COMSOL step by step. Let's start to implement our CV COMSOL model. The first is the model wizard. After starting the COMSOL software, we can click the model wizard button to start our model wizard procedure. And then in the space dimension window, we select the 2D axis metric. In the select physics tree, we can find out the chemical species transport and the transport of dilute species and click add. And then in the review physics interface window, we select the number of species 2. The default concentration appears in this table, C1 and C2. Here, we will change it to COX and CRED. OX and CRED to represent the oxidized and reduced forms of the species. And then we click Study. Because cyclic voltammetry is a time-dependent study, so we click Time-Dependent. And then Done. Right now, we finish our model wizard procedure. Next is the global definitions. In the model builder window, click Global Definitions, Parameters 1. In the setting window for the parameters, click the Load from File button. And we will need to browse to find out our CV parameters. And then click Open. So you will see that this table lists all the parameters we will use in this COMSOL model. If you want to modify the value for the parameters or want to add more of the parameters, so we can just modify using this table. Next is the definitions. We will use piecewise function in COMSOL to implement our potential time function. Right-click the definitions, find out the functions and the piecewise. So piecewise function will appear below the definition. Find out the function name, change it as an E. And for the argument, we'll change it as the T. We click Load from File button and find out the ET function CV. And we click Open. So this shows the functions for the potential time. And then in the units section, for the argument, the unit will be the seconds. Function units is the potential we set as the V. And we can click plot button to see our potential time function. We will write equations for Voltammetry model using variables in definitions. You right-click the definitions, find out variables. Under variables sections, we click Load from File buttons, and we find out variables text file prepared, and then click Open. And here is the equations of the Voltammetry model. So we will right-click the geometry and find out the rectangle. So the rectangle one will appear below the geometry one. In the setting window for the rectangle one, we will type electrode in the label text field. Electrode. This sets the geometry name as the electrode. And in the size and shape section, we'll type the ELRAD for the width, ELRAD. Let's build our model geometry 100 times ELRAD for the height. And this sets the electrode radius and electrode length to ELRAD at 100 times ELRAD. The value of the ELRAD is defined in the global definitions in the parameter 1. And we can go back to find out the value we set. So the electrode radius we set is 5 micrometer. Okay. And then we can go back to our electrode geometry. And then we can click on Build Selected. And then this shows the geometry of the electrode. So next is the glass geometry. We'll just follow the similar procedures. Right-click the geometry and find out the rectangle. And we can change the name for the rectangle 2 as the glass. In the size and the shape geometry, for the width, we'll change it as the RG times ELRAD. For the height, it's 100 times ELRAD. And then we can build all objects. This is the geometry for the glass. Finally, is the geometry for the solution. And we will right-click the geometry, find out the rectangle. We change the name for the rectangle 3 as the solution. In the setting windows, we can find out the size and the shape. For the width, we set it as 100 times ELRAD. And the height is 200 times ELRAD. And in the position sections, we can type negative 100 times ELRAD in the Z text field. And we can build all object. So you will see the solution geometry. We can click the zoom extents to see the whole geometry. So this is the electrode, this is the glass, and the rest will be the solution. Now let's start to set the physics of transport of diluted species. And then in the model builder window, we can find out the transport of dilute species, and we click it. In the setting window of the transport of a diluted species, we'll need to select the domain. In here, only domain 1 need to be selected. That represent our solution. And we'll click the domain 2 and remove from selection, and the domain 3 and remove from the selection. So you will see that the solution geometry will turn blue if you select it. In the transport mechanisms, we will deselect the convection because we'll assume our system is diffusion controlled. So you will see that our equations becomes this way. The first is the continuity equation, and the second is the fixed diffusion law. And then we can click transport properties. In the model input section for the temperature, we will click it, find out the user defined. We will define it as the TB. For the TB is a parameter we set in the global parameters. And then we scroll down, find out the diffusion coefficient. So we will change it as the D and D. We also define this parameter D in our parameters, so we can find out what we set. So for diffusion coefficient, this number is what we set. So we can go back to our transport properties. Then let's start build boundary conditions. First is the initial values. We can find out the initial values below the transport of down species physics. And then in here, the domain 1 is automatically selected. In the initial values section, we will type the CB for COX text field and 0 for CRED, that representing the initial values of the systems. We will set the concentration boundary and right-click the transport of properties and find out the concentration. In here, we will manually select the boundary. This one, and this one. This is the boundary 2, 10, and 11. In the concentration section, we will click the species COX and species CRED. For the COX at the boundary of the solution, that will be the same with our bulk concentrations. For the CRED, that will be the 0. Let's set up the electrode surface boundaries, and we will right-click the transport of dilute species, find out the flux. Flux 1 will appear below our transport of diluted species physics. And then, in the settings window of the flux, we will manually select our boundaries. In here, we will select the boundary number 4. This represents our electrode surface. You can also zoom in again to see. In the inward flux sections, we will choose the species COX and the species CRED. Write the equations of the flux. For the species COX flux, that is the negative Tf times COX minus Tb times CRED. For the species CRED flux, that is the Tf times COX minus Tb times CRED. Right now, we finished the settings for the boundary conditions. When the physics settings is done, we will need to build the mesh. And we find out the mesh one. And in the settings of the mesh one, we will need to find out the user-controlled mesh. You will see the size and a free triangular will appear below the mesh one. In the size, the predefined element size, we can select normal. After that, we can click Build All to see what it looks like for our meshes. They don't have enough numbers of the meshes at the electrode surface. So we will need to use Edge in the mesh. And we right-click the mesh one, find out More, click Edge. Edge 1 will appear below the mesh 1, and we can move it up. In the Edge 1, we select the electrode surface. Right-click the Edge 1, choose the size, and we custom the size. In here, we click Maximum Element Size. We set ELRAD divide 100. And we can click Build All to see what it looks like. So you will see more meshes are built at the electrode surface, and that is what we want. Right now, we finish our settings for the mesh, and the problems is now ready for solving. We can click Step 1 Time Dependent. In here, we will set the output times from 0 seconds to TEXP. Our TEXP is the parameters we set at the global parameters. So we can find out what number it is. In here, it tells us it's 100 seconds. Okay, we can go back to our time dependent. The settings in here means it will collect the data from 0 seconds to 100 seconds every 0.1 seconds. So the total data point will be collected is 1,000. And now we are ready to compute our results. Computation is done. A number of plots are created by default. So for example, the concentration COX and the concentration COX 3D. We will need to do more post-processing. So we right-click the derived values and find out the integration, line integration. In here, we will manually select the electrode surface. We can zoom in and select the number 4. In the expressions sections, we will load from the files, find out the results, line integration, and click open. This represents the current, and this is the potential. You can also find out these values from the replace expression. After that, we can click evaluate. A table will be generated. This contains the time, current, and the potential for our cyclic voltammetry. In order to get the CV plot, we will use the 1D plot group. We can right-click the results, find out 1D plot group. And then we right-click 1D plot group, find out the table graph. We will use the table 1 to generate our plot. For the x-axis data, we will use the potential. For the y-axis data, and we'll manually select the current. After that, we can click plot. A very beautiful CV plot will be generated. And then you can do few modifications to get the oxidation reaction.